So before I start the video, I just want to share something that I'm not a master programmer. I'm an aspiring one. So I do not have deep knowledge about the topic I'm going to share. I'm just a learner, and I like to share what I learn, and that is what this channel is about. I do not claim 100% correctness of my solution to the problem. So feel free to point me my mistakes. Uh, One tip, I speak quite slow because English is not my native language, so watching the video in a faster speed might be a good idea. So we're going to talk about recurrence relation resolution for multiple inputs. Basically, we're going to analyze time complexity for one divide and conquer algorithm. So I'm doing a MIT OCW course. This course is called Introduction to Algorithm, and you can check out the course in the MIT website. It's a free course, and the lectures are available in YouTube as well. Course content can be found in the MIT OCW website. So before doing this course, I was comfortable with analyzing time complexity of divide and conquer algorithm, which has a single input like this. This is the this is the recurrence relation of merge sort. So you can see here that it has only one input, but when I started doing the course, I came across a problem where I had to do recurrence. I've seen a recurrence relation for two inputs, so I had to consider two arrays, and to solve time complexity for a recurrence that has two different inputs. It can be a bit tricky. So let's see the question first, the problem. So we need to find out the asymptotic complexity of an algorithm with runtime t of n and n, where t of x and c, so two inputs, x and c is constant because c is less than or equal to 2. So basically, when the first input is relatively large, and the second input is not that large, it's basically very small, it's equal to 2 or less, so then the time complexity will be theta of x. When the scenario is opposite, when the first input is small, you can see here it is c is less than or equal to 2, then the time complexity will be theta of y. And for relatively large inputs, the time complexity will be theta of x plus t of x y by 2, because every time y by 2 is because every time we recurse, the second input gets divided by 2. So this is the problem, and to solve this, so we can rewrite the function like this: t of x y equal to t of x y by 2 plus cx. The original function was theta of x. We can rewrite it as cx, because we know that theta notation bounds a function from above and below. So and the upper bound and the lower bound is different for the function just by a constant factor, so we can write theta of x as cx. So what we have to do here is we have to find the value of this t of x and y by 2, and so we can substitute y by 2 in place of y in equation 1. So we need to find out the value of this. So time taken for t of x and y by 2 will be equal to time taken for x and y by 4, because we will have to divide the y input further. So it will become y by 4 plus cx. So this can be our second equation. So what we can do here is plug in the value that we have found for t of x and y by 2 into the equation number 1. So this will become this t of xy equal to uh, t of x y by 4 plus cx. So this will become plus 2cx, and we can rewrite it further as t of xy equal to t of x y by 2 raised to the power of 2. This we will see shortly why we have done this. Actually, we are trying to find a pattern here. So we are stuck in this thing again. So now we have to find out t of x and y. We have to find out time taken for x and y divided by 2 raised to the power of 2. So if you substitute y by 4 in place of y by 2 in equation number 1, in this equation, what we will find out is t time taken for x and y by 4 is equal to time taken by x and y by 8 plus cx. So basically the same thing that we did previously. So now what we can do is we can plug in equation number 4, this this equation into equation number 3, and this is what we will find. T of time taken for x and y is equal to time taken by x and y by 8 plus cx plus 2x plus 2cx, and this can be rewritten as this. We just added up this, and we can rewrite it further as this time taken for x and y divided by 2 raised to the power of 3, and we can give it a equation number of 4. So now we start to see a pattern here. Every time we basically recurse, we see that this 2 raised to the power of 2, and uh, the number of times cx gets incremented. So this number gets incremented by 1. So every time we recurse. So this is the pattern here. So this equation can be rewritten as t of xy equal to t of x and y divided by 2 raised to the power of n plus ncx. We can keep on dividing it by 2 and every time we divide it, this and this will get incremented. So what we can do here is, to find n, we need to calculate how many times we can divide the second input by 2. How many times till we hit the base case. So if I go to the previous slide for a bit, sorry, here is the base case. So we can see here is time taken for x and c. Basically c is 2. So when we keep on dividing the second input by 2 every time, there will be a time when the second input will be equal to or less than c. So then our the time complexity will be theta of x. So this is the base case here. So through this we can basically calculate the number of times cx will be multiplied. We can see this is a geometric pattern. Sorry, this is a geometric sequence. So first we had y, then we had y divided by 2, then we had y divided by 4 or y divided by 2 raised to the power of 2, then we had y divided by 8, which is y divided by 2 raised to the power of 3, and this will keep on going till we hit the base case 2, and this is the base case basically again. So if we solve the number of terms in this sequence, we will know the value of n, because every time we divide the second input basically by 2, we had seen that this gets uh, incremented, so we need to calculate that. So to solve the geometric series, uh, so a sub n equal to a sub 1 into r raised to the power of n minus 1. So r here is the ratio, and the way we find the ratio is when we divide one factor of the sequence by the previous factor of the sequence. So if we divide a sub 2 by a sub 2 by a sub 1, we will get the ratio. So this is how we find out the ratio, and this will be 1 by 2 here, so this will be half, and the we need to find the value of n, and well, a sub n is 2 because that's the base case, so we can solve for this. So 2 is equal to y into 1 by 2 raised to the power of n minus 1, and if you solve for this, we will find out that n is equal to log of y. I'm not going into the calculation of this here. So now let's plug in the value of n in equation 4. If we plug in the value, we will find this. This is cx because when it will hit the base case, we have seen the time complexity is theta of x, so the value of this will be, the time taken of this will be theta of x, so we can write cx plus ncx. ncx, the value of n is log base 2 of y into cx. So in theta notation we know that we get rid of the lower order term, so cx is the lower order term here, so we get rid of cx, and the theta notation becomes theta of x into log base 2 of y. We know that in theta notation we do not care about constant term, so this becomes the theta notation for the recurrence, and we can write it further as we were asked to solve for t of n and n, so the time complexity becomes theta of n log n. I hope this video was helpful.